We're going to be talking about highly automated physical systems and the security associated with that. And I call this system-aware cybersecurity because over the last 40 or 50 years, cybersecurity has focused on a mixture of perimeter security and network security, and much less so on application security for a variety of reasons which we'll discuss. But as physical systems start to become automated, they create a new kind of issue to deal with, and it's at the application layer. So we'll be talking about concepts for how one could address physical systems at the application layer. So let me start changing slides. Okay, so I want to start by saying that what we're dealing with is a mechanism for achieving system resilience. So resilience is defined as the ability to keep a system operating even when it's under some duress. And historically, this duress could be for the military, electronic warfare, weapons doing things to it, or it could be Mother Nature. And now the subject becomes, what about cyber attacks? And the nature of resilience is to monitor the normal way a system runs and to notice whether bad things are happening for whatever reason, and if so, potentially reconfigure the system so that it can continue to operate in the face of whatever it is that's disrupting it. And this continuing operation could be less capable than the normal, but it's sufficiently satisfying that one decides that it's worth doing. And the reconfiguration could be not only technical, but operational. That is, different people do different jobs in order to keep the operation moving. And so for resilience, it implies there's a monitor. That's this sentinel that Rick talked about. There's a process for reconfiguration. We'll talk about that. And for cyber attacks, in addition, we have the need to collect data as to what we've observed with this sentinel that could potentially be used for post-attack forensic analysis so as to discover where the actual attack occurred and what can be learned about it to correct it. And so I used this definition that was developed by people at the Idaho National Lab, and I added the red stuff. Their definition was done in 2009, and it wasn't related to cybersecurity. And so I just clarified, as it relates to this presentation, the red stuff. So if we go to the next slide, I want to talk a little about system engineering through my eyes and how it relates to resilience. So I like to talk about system engineering as addressing the integration of policies, processes, which account for human factors, technology, and data collection and analysis. So it's the integration of these things that together create a system. And we would like a system to be good and continuously improving. And system engineering combines these in a manner that hopes to be good and justifies the integration through sometimes mathematical analysis, sometimes through arguments that have a logical base, sometimes through simulations, sometimes through prototype trials. And so that's what the system engineering profession tends to engage in when designing systems. And so if we talk about security and cybersecurity, we have the issue of we're going to defend the system. That is, certain cyber attacks won't be successful because of defense. But we also can do resiliency, monitor to see a successful attack, and respond in a manner that's sufficiently quick and sufficiently capable so that we can continue operations. And so we have these two solutions at our fingertips. And to date, of course, I'll say almost all of the effort has been focused on defense rather than resiliency. But with the world that we live in today, one can start to see the need to recognize that defense can be a pretty hard thing to fully accomplish. But further, for physical systems, we'll talk about the outcomes that might be less acceptable than the ones that we have today. So the question we're asking is, does my system prevent anomalous events when they occur? Or respond to them in a containing manner. And what do I want to do about it? And the answer depends upon the consequences of whatever it is that we're imagining could happen, the likelihood of this happening, and the comparison of the effectiveness and cost of different solutions. That could be defense solutions, or they could be resilient solutions, reconfigurations. And this brings together the need to consider policy, process, technology, and data assessments to make a decision about how to complement defense and resiliency with each other in a manner that's most productive. So that's how I frame the top level version of this problem. So the next slide just wants to say that resilience is not a new topic by far. And I spent 10 years of my career dealing with nuclear weapon command and control. So you guys at Sandia, maybe you're too young to have bumped into me when I was doing this. And I also spent 10 years even before that on the air traffic control system. So those are two systems that have resilience built in. I'm not going to go through this entire slide, but I'll use one example from each of the lists to make what I think are important points. So for the nuclear system, in the early 1980s, I think it was 1982 or 3, there was a chip that went awry at the NORAD warning center that lit up the displays that made it look to a 4-star general like our country was under a massive attack from the Soviet Union, nuclear. This really happened. And he did what the protocol called for, which was contacted the head of the Strategic Air Command, who was in charge of the weapons, and they contacted the President of the United States to deal with response. And our doctrine was that we don't fire based on seeing things on a display, but in order to avoid destruction of things, could be submarines at their base or it could be bombers at their base, we move things out of harm's way as best we can and as quickly as we can so as to preserve our ability to respond. And in that case, we actually launched bombers, put them in holding patterns, loaded, and they were ready to respond should the country be actually attacked. And the doctrine was first weapon has to hit before we respond actually, rather than readiness to respond. And that actually happened. We loaded them, we put them in flight, and of course we weren't attacked. So it was a false alarm. After that, there were a lot of meetings, and I was engaged in them to say what the hell would happen. And a very important topic came up, and it was a 3-star general who said, gee, if there were no actual weapons coming, how do we see these on the display? Did the sensors send this information? And a major said, we'll check, sir, and he left the room, and he came back, and he said, no, there were no traffic information sent from the sensors. And he turned to me, the general, and said, Barry, do you always design systems where there's no input but there's output? Pretty embarrassing moment in one's life. And I said, oh, well, we can fix that. We'll put in a monitor to make sure that there's always input when we have output. He said, no. We'll set a procedure where we call up the weapon site, the sensor sites, and ask them, are there targets being sent? And that's what we'll do. And they did it, and they made that part of their doctrine. So you could say that was close to a zero-cost resilience solution. And you don't forget that. So the point is it was operational, not technical, and it was very low cost. So that's in the game, as well as what could be more expensive kinds of solutions. In the air traffic control system, I was involved in designing the airborne collision avoidance systems that became TCAS that are on airplanes today. And that was a backup to a failure of the air traffic control system. And we did quite a lot of work. I was a young engineer at MITRE leading that activity. And we demonstrated that this could, with actual flight tests, that this could really work, and it could build on the existing surveillance protocols for the radar, secondary radar system, which it does. But our algorithms didn't deal with multi-aircraft considerations. That is, if 2 aircraft seemed to be ready to collide, we could tell each pilot what to do automatically. But we didn't check to see if there was a 3rd airplane somewhere in the vicinity that could cause a problem. We didn't do that. And when we were ready to take this thing to actual do it, the Lincoln Laboratory said, gee, we can't do that. And they wanted to have a meeting, and we set up a meeting with not MITRE and Lincoln Laboratories, but the head of the FAA and his contingency, a contingent of people, Lincoln Laboratories and MITRE. And he said, the head of the FAA at the time, that this is a backup. It doesn't have to solve the full air traffic control problem. We'll take it solving 2 aircraft collisions. So I also always remembered that. The resilience solution need not be perfect. You're in a difficult situation, and you might have to live with what you're going to live with. And in that case, they decided on that. By the way, there's been no commercial mid-air collisions since those systems have been enabled. And there used to be commercial mid-air collisions. So just an interesting anecdote. So given that, if we move to the next slide, the important lessons that I learned from those scenarios is that solutions can vary from low-cost procedural to very expensive system designs that offer resilience. And you can decide to deal with this topic at the mission level, system of systems, where it's difficult to conduct a complete analysis and manage the dollars. Typically in the Defense Department, for example, they buy a system one at a time. One at a time, they call it a system, but it's a subsystem of a system of systems. They don't have control over all of the other systems to redesign them. So it would be desirable to be able to do that, but it would be quite complex and difficult to manage. On the other hand, if we deal with only the one we're buying or improving, there may be better solutions that we don't use that could have been augmented through these adjoining systems. So you have this somewhat of a difficult situation to manage, how you deal with the system systems, if at all, and what you suffer and what you gain. Another thing that our work has shown, and I'll talk about later, is that we're responding to what we hope will be rare events, disruptions of physical systems. And operators, as I said earlier, will need to do different things than they might normally do. And so how do you get them ready for that? And it's different than what we did with the nuclear weapons, where we did train operators to do different things, in that these were physical things that the operators had intuition and experience with. Our experience in dealing with cyber attacks is there's no experience and there's no intuition. In fact, there could be very misleading intuition, and I'll come back to this. So that's an important thing, how you deal with the humans who are going to be part of resilience. And then once you get to the point where you say, you know, I really want to do this, what's this? So we're dealing with disruptions of system functions. A system can have a lot of functions, not a million, not a physical system doesn't have a million, but it can have 50, 100 that are important to you. So how do you decide which ones to be resilient with? And how do you determine when to use defense versus resilience as your solution? So now you're into the red side of things. What are these anomalies that attackers can create and will want to create? And which ones do I want to consider as more likely than less likely, and more damaging than less likely damaging, and deal with them? And then what do I do about my legacy systems? So you have all of those to deal with if you're going to address this problem. So that provides a context for, okay, we're in the resilience business. We better be ready to talk about those things. Now I want to say something about our readiness as engineers. So cyber attacks, as I said earlier, because of the history of what the attacks have been and what the solutions have been, have addressed the perimeters and the networks, but not the applications, for a variety of reasons. I'm not going to run through all the reasons, but they're listed on this slide. Well, this means that our engineers who know a lot about cybersecurity typically don't know about the applications that underlie the perimeters and the networks that serve them. So if you go to a cybersecurity engineer and say, gee, tell me how the air traffic control system works, they don't know. Not in enough detail to deal with it. They know it's bad to allow access to the system, but they don't know how it actually works. And if you go to the designers of the air traffic control system and say, gee, how would you protect? They don't know much about cybersecurity. That's something someone else does at the perimeter of the system. So we don't have a lot of engineers who deal with both. And that's a starting point that has a 50-year legacy. So we have to manage that. And I won't give a speech on this, but being at a university, I'll say universities aren't prepared to help us deal with this because we separate departments. Mechanical, electromechanical engineers don't learn about cybersecurity, and cybersecurity people don't learn a lot about electromechanical engineering. And the professors who deal with it have never been exposed across these borders in their careers. So we're not really quite ready for this, but the subject's ready. And while we yak about it, I'm not going to run through this list, but a huge amount of money is being spent today in our country and in the world on advanced automation for physical systems. Cars, unmanned air systems, digital factories, 3D printers, Internet of Things, and all of these are subject to potential cyber attacks. And, go to the next slide, many of the concepts for why these are being invested in relate to economy. Not many, they're primarily related to economy. I want to remotely control things. I don't want to have operators have to be with the physical system. Cost reasons and accessibility reasons. I want to deal with logistics by collecting data from these physical systems and doing maintenance based on use, not based on hours. Use being many dimensions. The temperature it was used at, the loads that it was dealing with, the continuation, the continuity of use, and other factors. So I want to collect this data. So I'm connecting to the physical system in a more dramatic way than we historically have. Health management. I want to manage a factory by monitoring the various machines. And if I see something is going down a path that's likely to fail and cause a failure in the near future, nothing to do with cyber attacks. I might reconfigure how I run the factory so I can deal with the orders I have on hand. So people are going down that path, but the same path could relate to cyber attacks. That is, people get the data and inject information and software into the health management system. So all of this opens up new cyber attack possibilities. And as you probably know, we not only have attacks through perimeters and networks, but we have supply chain attacks. We buy stuff from other people who could put stuff in it. And we have insider attacks, maintenance people, other people who could do stuff, people who deploy weapon systems who could do stuff. So we have lots of different kinds of attacks. And tampering is a lot harder to deal with when the microelectronics associated with tampering can be really hard to first visually see, but even hard to detect given their footprints. So we have an expanded world that we face to deal with physical systems and the applications. Well, given all that, when I started into this, which was about 2011, 2010, I don't remember, and it was actually the DoD came to me, and Stuxnet had occurred, and there had been a UAV that was stolen from us, and we tried to kill all the electronics in the system and couldn't. And I don't know this for sure because I didn't have the clearances, but about every time I met with a whole set of people, they'd always say, and make sure the kill switch works. So I suspect something went awry with the kill switch, and they were worried about cyber attacks. So they said, Barry, why don't you work on physical systems? And my first reaction was, gee, those must be really hard. But it turns out they have a lot of things that are easier than information systems. They're much more limited in scope, fewer functions, less distributed. The laws of physics still hold. In logical systems, there could be illogical systems as well as logic we don't know about. There's less software, not trivial amounts, but less. And less physical states than there are software states. So when I monitor, I could monitor some software states, but also physical states of the system to determine whether things are not functioning logically. But given all that, on the other side of the coin is that successful attacks can kill people. And we haven't really faced that in a first-order way with information systems. And reconfiguration requires immediate response. We don't have 2 months to patch. And we have to deal with patching as well. What do we do about patching, given it could be reused and physical harm? And we need operators who are confident about what they're doing, and I'll come back to that. And given zero-day attacks, how do we get them ready? And in addition, we don't have any gut feeling for this topic. In fact, the gut feeling that we've seen is that the implications of a physical cyber attack are that there's something physically wrong with the system. The battery is broken, or something like that, or its motor is broken, or something like that. Not that it's a cyber attack. And as I said earlier, the people who are going to design solutions have to know about electromechanical systems and cybersecurity, and we have a workforce and education issue on our hands. So that's a long introduction, but I thought it was worth it so that you have a sense of the scope of what needs to be addressed. And now I'll start to talk about what I call system-aware cybersecurity. Okay, so that's a name we coined. It's work that's been funded by the DoD and through the Stevens Institute's System Engineering Research Center. Other people have funded us as well. You'll see that NIST has funded us, the Army has funded us, the Air Force has funded us, companies have funded us. So we've had a good amount of funding on this topic. And so the idea is we'll add a layer of security to protect the physical system control functions through resilience mechanisms, monitoring and reconfiguration. We'll monitor for illogical system behavior. And if we detect illogical behavior, reconfigure for continuous operation. So let me say one thing at this point about illogical, and I'll come back to that. So think about adaptive cruise control in a car. I don't know if you know what adaptive cruise control is, but cruise control is, as you know, you set the speed that you want the car to automatically drive at, and it drives at. Adaptive is the car in front of you is going slower than you. So your car automatically slows down to his speed. And when that guy goes away, it re-speeds up what you set into place. So now imagine I'm monitoring this subsystem, this function, and I notice that the sensors say I'm closing on the car in front, but the control system is speeding up your car. And I'm monitoring the acceleration and brake pedals of the car, and they're not being applied by the operator. I can deduce that something is illogical here. I'm not positive what the exact cause might be. It could be a soft failure of the sensor, for example, it's not just broken, but it could be a cyber attack. And I could have other sensors to confirm what's going on and help me decide whether I think it's a cyber attack. So that's the nature of illogical. The solutions that we've addressed for response build on cybersecurity, fault-tolerant system design, and automatic control technologies. So I'll talk more about these a little later, but a principal concept in resilience is diverse redundancy. So instead of having two Cisco switches backing each other up, I have two different manufacturers' switches backing each other up. They almost do the same thing, but they're designed differently, so a cyber attacker would have to create different kinds of attacks to take out both. And of course, I can go to triple redundancy and so on. And so diverse redundancy is an important thing, and there are other things that we'll talk about. The monitoring for illogical behavior we do through what we call a Sentinel. So it has software to both collect data, and I'll show you how that's designed, and to make evaluations of illogical behaviors. And the argument that we've used, and over these years in doing lots of rapid prototypes, operational prototypes, is held up, is that the software required to monitor functions is trivial. And in fact, they've been 300 to 500 lines of code. So I could build 3 different versions. Make my Sentinel diversely redundant. And I could do other things, put them on different computer boards, which could be low cost, put them on different software, use different software languages with different operating systems. So I can add diversity to make an attacker's life more difficult. So later I'm going to tell you our criteria for good is that what it takes us to do is less troublesome than the trouble we create for an adversary. So we're not claiming we're going to prevent anything, and we're not claiming that we're going to perfectly deter things. All we're claiming is that attackers will be less happy if we do this than we are unhappy about having to do it. And that's the criteria, that we shift the value from being oriented to an adversary to being oriented to the defender as best we can. We address insider and supply chain attacks as well as network and perimeter attacks. So our approach is not to say, oh, here's an attack they could do, to say, here's a consequence they could create. How would you reconfigure your system so that it can continue to do that function in the face of an attack that we don't know the details of? We just know that it's making the sensors and the control system not act in a continuous manner. What can we do? When we started, people said, gee, you know, this is going to cost a fortune. Every one of these systems needs custom designs for how you're going to monitor and reconfigure. That's true. But it turns out that the concepts can be reusable. And I'll go through a whole bunch of reusable, what we call design patterns, for monitoring and reconfiguring. And so you don't have to start from scratch each time to say, hey, what would I do? You can say, I have a whole bunch of design patterns that I continue to add to, that I have to configure for the specific system in question, but I don't have to start from concept. I can start from specific design. And given the earlier comments I made about the scale of these monitoring solutions, makes them economical. So that's an argument. That's not a proof. But I'll show you that we've done a lot of rapid prototyping that have convinced us that there's a lot of merit to that argument. It's probably not 100% true, but there's a lot of merit to it. Back to the question of, so what solutions do I employ, given that there could be a host of them that seem attractive? And here we get into, and what we've been doing is using model-based analysis, and where we compose a system model for the system to be protected, and use attack tree tools and other tools that we're advancing to help us decide which ones give us this advantage over the adversary. So we have red teams, we have blue teams, we have a sequential evolution of conceptual level design to more detailed level design to model-based analysis, and finally implementation and testing with both red and blue teams. So that's the path we've been taking. And I'll give you some examples beyond the one I gave you of illogical control. So one of our prototypes was UAV. One of the things we did there, and I'll say a little more about it, was, let's say someone changes a navigation waypoint. And let's say we're operating in a doctrine where only the operator can do that, and he has to communicate to do that. But we see no communication on the aircraft, but the waypoint changed. We're monitoring the waypoint. Or we do see a communication, but we're also monitoring the keyboard of the operator. We didn't see him make an entry. Well, something's awry. The automobile, I gave you the example of collision avoidance or adaptive cruise control. We've done 3D printers. 3D printer, the material I select is not the material that would be called for, or the temperature, or the whatever is wrong. Fire control systems. The operator pushed a button, but the weapon didn't fire. The operator didn't push a button, but the weapon fired. I got it, Rick. Okay, so let me go to talk about the techniques for design. So cybersecurity provides ideas like data provenance. Does the data come from where it's supposed to? So I can monitor that. What we've done for defending our Sentinel is not only have diverse redundancy, but we could dynamically hop which configuration is dealing with monitoring and reconfiguration, and changing every 2 seconds which one is managing that, so that an attacker would have to create attacks that crossed the diverse set of design as well and did it every couple of seconds. The middle one, let me see if I can get rid of this. Okay, fault tolerance, we have the diverse redundancy. We also have voting. So I can have 3 redundant elements, and if 2 of the 3 agree on the state of situations, but one doesn't, we could decide to kick out the one. Automatic control. So one of the things we could do in Stuxnet, the operator was seeing the speed at which the reactor was rotating, the centrifuge, and it was modified. Well, we have other sensors that weren't measuring speed that could have been used to give an indirect. So, for example, if the temperature of the centrifuge is related to the speed at which it's turning, I could say, gee, it couldn't be at this temperature and turning at the right speed. And it discovered indirectly that what I'm seeing is not accurate. I can use state estimation techniques with multiple sensors to estimate the integrity of the important states that I'm directly monitoring. I can also have an ability to monitor what I think are the equations governing the system as I'm observing it operate, the dynamic equations. And if it's not the equations as I know them to be, I could decide someone's tampered with the system. So I have methods like that. And when I employ these methods, I'm forcing an adversary to understand how the system works to a level of detail that I have. Forcing to develop synchronized exploits across multiple subsystems. I force them to corrupt multiple supply chains. So do I win? I have to decide on that. I don't know if I win. But the point is, I'm putting more pressure on our adversary than otherwise would exist. My favorite design pattern from this list, there's a lot of them, and there's more, is parameter assurance. So let me say something about parameter assurance. So when we design automation systems, as you well know, parameters are used to change as thresholds. So in a radar, the threshold for detection is set as a parameter, and we make it a parameter so we can change it. And same for SIGINT systems. And those govern misdetections and false alarms. Well, if someone changes those parameters, he changes the way my radar works or my SIGINT system works. Smart systems have modes. And so if I change the mode, it's going to operate differently than I'd like it to. Navigation and waypoints, tracking algorithms, responsiveness to changes in position and velocity, communication systems, power levels for communicating. All these are parameters that I can adjust through a cyber attack. Very simple cyber attacks. I can monitor them, and I can decide then how to deal with them. Okay, so we've built many prototypes. UAV, we actually flight tested in an airport in Georgia. Automobile, we did it with Virginia State police cars. Policemen had no ideas what were going on. Did an exercise dispatching them. 3D printers, we did that with NIST. Physical plant control for a ship. Multiple operators control multiple functions on a ship that are physical. Not only weapons, but the toilets, air conditioning, all that stuff. And the communication switch that connects them to the plant becomes a topic. We've done a couple of weapon systems with the Army's Armament Division at Picatinny Arsenal. Weapon control, situation awareness can all be fooled with, and then one can have resilience just to address these. And now we're at the point where we've initiated an effort for the Army starting to implement, down a path to implement this in a future weapon system. I'm not allowed to talk about the weapon system. Let me change to human factors. Okay, so when we did our flight tests in Georgia, we did it with a totally automated capability. That is, the monitoring detected something, and when it detected it, it switched the way the airplane was configured. And questions arose, well, how will the military like the automation? And so we teamed with MITRE, my old company, to do a simulation-based experiment at Creech Air Force Base. Creech is in Nevada, and it's one of the most depended upon for controlling UAVs in the Middle East. And we created a rendition of the control systems that they use. It's for the operators to see what would happen under a scenario and what they would see from the Sentinel and what would happen and what they would do. So we did that. And MITRE rendered the display that they actually used. So the picture you see is the video coming down from the UAV in the area it's surveilling. The picture above it is just the version of air traffic picture of where that airplane is relative to the geography below it. Those message displays on the side, turns out that the operator can push a button and contact his doctrinal support repairman. If something seems wrong with the airplane while it's still in flight, he can actually contact the repairman and help him, waggle the wings, try this, try that. So he has all that. And we added to this in the upper right, the Sentinel's display of, there's an attack, here's what it is, and here's what the reconfiguration is that's taking place, and here's what you have to do. So that's what we did. And what came out of that? A disaster. The pilot said, it can't be automated. You don't have the context of battle. And we got to account for the context. Only we have that. So we have to be in the loop. That was the first thing he said. I'll tell you later that the Army said we can't have the operator in the loop. They're too busy. It's got to be totally automated. Interesting. The Navy had a third version. The operator said, gee, we want to, just like the repairman, we want to contact a guy who knows a lot about cyber attacks and talk to him. What would you ask him? We don't know. What if we put a guy at your base? We wouldn't believe he knew about cyber attacks. Sort of an interesting response. We want to just take the airplane home because how do we know there's not a second attack that's even more damaging that they don't want to reveal? And they want to get away cheap. So maybe we ought to just get the hell out of there. Oh, gee, how much time do we have to respond? Can we think about it for an hour? How long do we got? We hadn't done any work on trying to automate giving them a response time. We just assumed rapid response. What about the airplane in the hangar? Same kind of airplane. We're going to use that tonight. What are we going to do? All very interesting questions that we hadn't opened the door to when we started this, when we did this experiment. This is 2014. Okay, we've got to do more work. So we teamed up with the Air Force to look at doing more work on human factors. And the subject that came to the fore was, gee, how do we select operators and train them? And people had done work at Wright Air Force Base in the research, AFRL, associated with operator suspicion. That is his nature, or her nature. You know, they're a suspicious person or not. And people have developed criteria that through a Likert scale kind of test can say you're more suspicious than I am in your nature. And then the question is, can we use things like that to say we don't want suspicious guys, or we want suspicious guys? And frankly, none of us knew what we wanted. So we did an experiment. And the experiment was, we'll bring in, and we actually used a large team of operators. I'll show you the numbers in a minute. We gave them Likert scale tests, so we could say what their suspicion level was based on prior research done by others. And then asked ourselves, do we like suspicious guys or not? Does their level of suspicion change as they get some more experience? So we actually redid the test more than once as we had run different kinds of experiments. And do we like autonomous sentinels, or do we like humans in the loop based on what we discovered? So that was what we tried to deal with. We got 32 airmen, a sort of miracle that we actually got access to 32 Air Force people to do the experiments with. And we ran 256 experiments. what if the consequences are different? So we did an experiment that dealt with training and someone disrupting a training exercise, and we did an experiment with an actual scenario in the Middle East, and exposed the operators to both those as part of the experimentation. And what did we learn? We learned that the people who were more suspicious were worse, because there's other data than what Sentinel provides available, and they're terribly curious about being sure they're doing the right thing. And so their response times were greatly delayed compared to those who were less suspicious. Also, as the consequences of their decisions went up, their delay times went up, more suspicious people. So we got to a point where the delay times were a major consideration in separating out operators who did better from operators who did worse. And that raises the whole question of what other human factors relate to outcomes. And so we're working with the Air Force and trying to address that. And the next chart just simply says we got to do work. Okay, model-based analysis. What we're dealing with there is we got solutions to pick from, defense solutions and resilience solutions. So it's not that we're stuck with one or the other. My general view in dealing with these kinds of matters is they're available to me, both. What do I want? So for defense, we're going to prevent something from happening. But depending on what that thing is, we have to know what it is. And there may be a lot of different points at which the same effect could occur that I have to defend. So I could have a wide proliferation of things I have to do. If I'm going to just stick to perimeter and network, I'm not going to deal with the application. I'm going to assume we're going to deal with the application. So defense, I can't deal with too rich a set of an attack surface and successfully do defense. Resilience, I can deal with a more complicated attack surface, but I'm not going to defend. I'm going to have consequences that occur based on the delay in my responses and the nature of my response. So that's what I have to decide on. Which of these do I prefer for which functions, for which system? And how do I decide on all that? And so what we've done is we put together a team that consists of the Army, the Software Engineering Institute, Virginia Commonwealth University. They have special knowledge associated with the use of attack trees, and the lead person has a lot of experience red teaming in the military, and UVA. We're looking at a mission-based weapon system. Mission-based meaning it's the weapon system, but it's tied to external systems that support it. And we've created a mechanism for deciding on how to design the system, concurrently design the security and the system. So we have a war room that's blue, that's providing operational judgments about consequences to be avoided. We have a red war room of attackers who want to disrupt the system. However, their experience tells them they'd want to disrupt it. In some cases, it could overlap with what the defenders thought they cared about. In other cases, it might not. We can define defenses and resilience solutions based on the use of design engineers. And then we can, as we get more detailed in our analysis, switch to model-based analysis. And we're using SysML to represent the system, and the representations are related to the attacks. So, they're going to attack the automated cruise control. Let's show a system representation of automated cruise control in a lot of detail. We don't have to show other things about air conditioning your car in a lot of detail. So it's going to be related to the cyber attacks. And let's build an attack tree model, and we're using Secure IT Tree as the model, to look at different ways the attacks could occur. And let's compare them and decide on the cadre of solutions that best suit us for the budget that we have. So that's the path we're going in, and we're learning as we go. So it's sequential, and we've decided we have 1 year, which from my experience, which is pretty extensive in military design of systems, they take a year to design a system from preliminary design to the final design to be implemented. Not final, but the design to be implemented. And so we have to mature our integrated view of security and design over that year period. And we're going through that process right now with a hypothetical system. And of course, we need a multidisciplinary team of industry, government, operations people, cybersec people, electromechanical design people. And so we're learning how to do that and see if we can create solutions that are more satisfying. So I'm going to end my talk by saying there's a need and opportunity for resilience-based solutions. That's the first thing. That defense by itself can be enhanced. And for physical systems is the focus I'm talking about. I'm not positive what we can do about resilience for information systems. I've done some work in this effort related to cloud computing with some interesting ideas, but the scope of these systems and information is so much bigger, and the function so much broader, and the logic so illogical or not known to enough people that it's a much more imposing problem. We have to not only deal with technology, but human factors and model-based analysis. So we have that burden if we're going to do resilience. And we need to take a broad view regarding the importance of these requirements. And broad to me includes the topic I touched a teensy bit on, education, and a topic I didn't talk about at all, but policy. How do I certify operators? How do I arrest people who do attacks? For the military, what do I consider warfare? There are a ton of policy questions. And so all of that has to be concurrently learned about as we step up to this table. So with that, I've used up my time.